Welcome to the Rasa Reading Group with me, Dr. Rachel Tapman. I realize I do not have to introduce myself because I got my name on the screen. Why do you have your name on the screen, Rachel? Because sometimes I'm so tired I don't remember names. And I figure y'all are in the same boat. So today we're going to be starting a new paper that actually came out last week. I was feeling I was a little bit behind the curve in getting around to this paper, but I don't think that's true. This was last Monday, and we got to it pretty quick. But there's been a lot of, if you're on machine learning Twitter, there's been a lot of discussion recently about transformers. I mean, that has been the case for, this past, 4 years in there. But there's been a lot of discussion about specifically what do you need in a transformer? So the transformer paper of Vaswani et al. 2017 very famously is entitled "Attention is all you need" and proposes this new architecture where attention is the only mechanism. And there have been several papers recently suggesting that you can use things other than attention and still get the same sort of performance that you would from an attention-based transformer architecture. And the reason why that's exciting is that attention requires 3 matrices, right? The query, key, and value. And all of the values in each of those matrices are learned. So you have a lot of, I say matrices are tensors. So you have a lot of learned parameters. And the more learned parameters you have, the more data you need, the more, training time you need. And also, the more liable your model is to fall to over-parameterization, which is the idea where basically you have too many things. You have too many, items to learn. What's a good way of... So imagine you're watching on, you're watching a video on, a super high definition television, right? But the video is in 360p. So there's not that many pixels and it sort of has to make some up to be in the middle. And that's sort of the problem with overparameterization, is that you have more ability to capture signal than you have actual signal. And as a result, you get weird overfitting and it's just very expensive. So I don't know. I hope that was a pretty good introduction to overparameterization and why it's a problem. And it's expensive and models are big. So what if you didn't use attention? What if you used something else? And there's been work on Fourier transforms, which you may be familiar with if you have much background in signal processing, or say speech. An old friend of mine from before times. And this paper, which is out of Google Brain on MLPs, MLP here being multilayer perceptron, your classic deep learning architecture, the one people show you slides of, where you have the input layer, the hidden layers, it's fully connected, and then the output layers. I don't think in the paper they ever say what MLPs are, so that would be my first piece of advice to the authors, because this is a preprint, is you should probably define MLPs at some point, because that is an ambiguous acronym, and it means other things. So without any further ado, let's get into it. Let me make sure I can actually see all the chat. Hi, Smetrio. Sorry if I'm saying that wrong. Welcome. And let's zoom way on in so I can read this. So the paper, again, it's a preprint. I assume it has been submitted somewhere, but I don't know that for sure, is by Hanxiao Liu, Zihang Dai. I know my tones are wrong. I'm sorry. Probably also some of the sounds are wrong. Feel free to correct me. David So, and then Quoc V. Quoc V does a lot of work on sort of transformer architectures, and I think this is a lot of his research group, so you may be familiar. I think EfficientNet was Quoc V's paper. Let me double check that before I say a wrong thing. Tan et al. Yes, okay, I would like all the authors. Yeah. So EfficientNet paper is Minxing Tan? Ooh. And then Quoc V, so you may be familiar with EfficientNet. Hi, Anupam. Welcome to the stream. All right, let's jump in. Transformers. that's going to be the Swanee paper, have become one of the most important architectural innovations in deep learning and have enabled many breakthroughs over the past few years. Here, we propose a simple attention-free network architecture. So transformers, famously, it's all attention. This one, zero attention. gMLP, nope, gMLP, there's no N in there, based solely on MLPs with gating, so multilayer perceptrons, and show that it can perform as well as transformers in key language and vision applications. Spoiler alert, I'm not going to read the vision sections. Our comparisons show that self-attention is not critical for vision transformers, as gMLP, there's no N in there, can achieve the same accuracy. For BERT, our model achieves parity with transformers on pre-training perplexity and is better on some downstream tasks. On fine-tuning tasks where gMLP performs worse, making the gMLP model substantially larger can close the gap with transformers. In general, our experiments show that gMLP can scale as well as transformers over increased data and compute. Interesting. Okay, so you made it bigger. But yes, so I would say the core point of this paper is that, in fact, you can use things other than attention and still have successful models. Can I just get this right? Oh, I have more space. Whoop, there we go. Fabulous. Can I get one more? Nope. I'm just trying to make it as large as possible. And I think that's about as large as I can get it. Okay. Transformers have enabled many breakthroughs in natural language processing, which is not abbreviated, have been shown to work for computer vision, and have been shown to work well for computer vision. Thanks to this success, transformers have largely replaced LSTM RNN, so long short-term memory RNNs, which recurrent neural networks, which I believe have a gating mechanism. So I think this is taking like bits of the LSTM mechanism. Although, right before transformers, it was really LSTM RNNs with attention, and that were bidirectional, that were state-of-the-art in a lot of NLP tasks. Honestly, they still hold state-of-the-art in some NLP tasks, but it's definitely not the like fancy architecture everyone's talking about. Hi, Sarav. Welcome, welcome. The transformer architecture combines two important concepts. One, a recurrent free architecture which computes the representations for each individual token in parallel, and two, multi-head self-attention blocks which aggregate spatial information across tokens. On one hand, the attention mechanism introduces the inductive bias that the model can be dynamically parameterized based on the input representations. On the other hand, it is known that MLPs, multilayer perceptrons, with static parameterization can represent arbitrary functions with limitations on the structure of the MLP. So like a multilayer perceptron where the hidden layers are narrower than the input layers cannot describe a non-congruent function. So yes, but caveats. And that paper was from AAAI, maybe? I can find that citation if anyone's really interested. It therefore remains an open question whether the inductive bias and self-attention is essential to the remarkable effectiveness of transformers. Yeah, so basically they're saying, hey, you can learn your parameters, online from your data, which that's one of the big, that's why it works, right? But from a practical standpoint, the reason why transformers are so appealing when you've been working with RNNs is because RNNs are sequential model, right? So you have to do time step 2 before you do time step 1, and that introduces a bottleneck because you have to step through things. Because transformers look at everything at the same time, you can parallelize to a greater degree. So clock time can be faster for training a transformer if you have the ability to parallelize your computations. If you don't, for example, have a GPU or several GPUs or TPUs or whatever it is that you're using. I believe the original transformer paper used GPUs, and I think BERT used TPUs, but don't quote me on that. I'd have to go check. Where was I going with this? you can train a model faster in terms of like the human perception of time, but not necessarily like in fewer operations. Also, I know I'm talking fast today. If y'all have questions, please jump in the chat. Yeah. Blah, blah, blah. Here we study the necessity of self-attention modules and key language and vision applications of transformers and propose an attention-free MLP-based alternative to transformers, which consists of channel projections, spatial projections, and gating. So this is their specific architecture that they are proposing to replace multi-headed attention. So they're not replacing the whole structure, just the attention part. Diriush, sorry if I'm saying that wrong, says, when was the first time the notion of attention started? Ooh, that is a good question. Attention has been around for a while. I think, let me look at the Daswani paper. Because I'm pretty sure they have one of the canonical I'm pretty sure they have one of the canonical citations. So this was the paper that proposed transformers. Let me just get this going. It's been a while since I read this. No. Oh wait, the Bengio paper. I think this might be the canonical citation. So 2014-ish. That sounds about right, because it was around 2016 that bidirectional LSTMs with attention got to be like the hotness, which they no longer are. It's a very tiring field to be part of because you constantly have to be learning new stuff. Yeah. Sarav says it's this paper, neural machine translation by jointly learning to align and translate. Yeah, that one. This one, which is from Core 2014, which is, I don't remember. Conference on Representation Realness. I don't remember. Probably not that. Computing Research Repository? Oh, okay. Maybe this is just like a place where the paper was put and not actually the publication venue. Anyway. So hopefully that answers. Anupam, it started with the paper Attention is All We Need, probably. No, it didn't. It didn't. So that paper proposed the transformer architecture, which used attention, but attention had already been around and was being used in state-of-the-art models. So it basically removed things other than attention from the models, like recurrent neural networks and long short-term memory. Yeah. And I've lost my chat window. There we go. Yeah, no, and so Sarav is right. Oh, but good question. So this is their proposed replacement for the attention mechanism, the multi-headed attention mechanism. Channel projections, spatial projections, and gating. So gating has also been around for a while, and it's actually been a while since I looked at gating. I would need a refresher on exactly what it is, but I'm assuming this paper will give that to us. We experiment with several design choices for the MLP-like architecture and find spatial projections work well when they are linear and paired with multiplicative gating. We name the model gMLP because it's built out of a basic MLP layers with gating. Rachel, what's spatial projection? We'll find out. We apply gMLP to image classification, blah, blah, blah. They applied it and they got results. I'm sure we'll read that in more detail. Oh, no, this is all image. We're not going to read that in more detail. Y'all are welcome to. I'm not going to. They also applied it to masked language modeling in the BERT setup, so guessing the word that fills in the blank, which is the way that BERT is trained. one of the most well-established applications of transformers, and find that it is as good as transformers at minimizing perplexity during pre-training. Perplexity is, I always get perplexity and entropy backwards. Basically, it is how well your model is characterizing the predictability of a string pattern, more or less. Probably not the best explanation, but our experiments indicate that perplexity is only correlated with model capacity and is insensitive to the presence of attention. Okay, now, interesting. So you don't need attention, is what this this paper is proposing. And perplexity is usually used as a measure of language models. So I believe the BERT paper reports complexity. The transformer paper, it's a machine translation paper. I don't remember if they report perplexity or not. Yeah. Anupam says, thanks. Yeah, you're very welcome. You're very welcome. As capacity increases, we observe that both pre-training and fine-tuning metrics for gMLPs improve as quickly as for transformers. Sorry, this is tripping me up, because NLP is it's a thing I say a lot, and also MNLP is a slice of the alphabet, which is something I also have memorized. So it's very hard not to stick the little N in there. This is remarkable because it indicates that gMLPs scale just as well as transformers despite the absence of self-attention, and any performance gap can also be offset by training a larger model with increased data and compute. I guess that's interesting from a theoretical perspective. I think what appeals to me more is that I think the gMLP approach starts with fewer parameters. So you can start with a smaller model, and if it gets you where you need to go, you don't need to increase size. We start with a standard 256 batch size times 1 million step training setup, as in the original BERT. Our MLP-like model achieves 86.4% accuracy on MNLI and 89.5 F1 on Squad V1.1. This is a question answering data set, and this one is natural language inference. So given two statements, figure out if they are contradictory or one implies the other, that sort of thing. Note these are comparable to the results reported in Devlin et al. Obtained using transformers. That's the BERT paper. Hi Alejandro. And Amina, hey, welcome. And Sriram, welcome. Santush says, also there's NLP. Yeah, it's, I would say it's very hard to say. For me at least. Note these are comparable, we read that. For BERT's fine-tuning, transformers can be more practically advantageous over gMLPs on tasks that require cross-sentence alignment, e.g. by 1.8% on MNLI, even with similar capacity and pre-training perplexity. This problem can be addressed by making gMLPs substantially larger, 3 times as large as transformers. No, I don't like that. Transformers are already very big. A more practical solution is to blend in only a tiny bit of attention. A single head attention with a size up to 128. Okay. Is sufficient to make gMLPs outperform transformers in all NLP tasks we evaluated with even better parameter efficiency. Yes. I love to hear about that. Love to hear about the parameter efficiency. Yeah. So what they're saying is, you can do it without attention as long as you have a lot of parameters, but you can reduce the total number of parameters you need if you add a little bit of attention, and also their proposed gated multilayer perceptrons that we haven't looked at yet. That I like a lot. The improvement is sometimes very significant. You can always tell when it's a person who's not a statistician discussing their results, e.g. plus 4.4% on Squad V2 over BERT large in our experiments. Okay. I will say that it is good to see these results. I am conscious of the fact that this is really playing into sort of like a larger leaderboardism structure of evaluating systems in, in machine learning in general, and Making the number go up doesn't necessarily mean that the model is going to work better for you in your situation, but it's good to know. Amina says, what is MLP and gMLP? Good question. So MLP are multilayer perceptrons. I'll pull up a diagram and you'll be like, oh, actually, is this? No. All right, let me pull up the thing. Also, they never define it in this in this paper. All right, and let me add some qualifications. Machine learning. You'll recognize it. So like the come on over. Multilayer perceptron is sort of like this architecture that you've probably seen when you have the input layers, you have the hidden layers, they're fully connected with, you know, weights and biases, and then you have your output, which could be, you know, multiple classes, weights across classes, or you could, you know, do softmax and have one out, or, you know, whatever it is that you're doing to get your output from your model. So this is the multilayer perceptron. It is sort of the most basic architecture in deep learning, and what makes it deep is that you have multiple hidden layers. Right? So if you've been in machine learning for a while, you've probably seen this. Yeah, also feedback for the authors, please define the term at some point. The gMLP is one that they are proposing in this paper. Yeah, is one that they are proposing in this paper that we have not yet looked at, and they are adding a gate to it. And it's been a while since I looked at gates, but gates are an existing piece of the architecture that you will see people using in different papers. Yeah. Pleomax says it's a dense layer structure. Yeah. Mm-hmm. Yeah. Oh, and also Santush jumped in there. Thank you. So, good question. Thank you. I can always rely on Amina to ask great questions, which I really appreciate. All right. Yeah, so far they're saying, hey, we're getting results that are comparable to transformers. We can get results that are better if we make our model really big. But the other thing that we can do is can take a little sprinkle of attention without that many trained weights and get better results. And that's what I like to see. I like to see reduction in the number of trained weights. I like to see smaller models, and I like to see models that work well with less data. But I don't think that's the point of this particular paper. The effectiveness of gMLP. Something tells me I'm going to have to say the name of this architecture a lot, and it's going to be rough for me. The lack of benefits of self-attention and vision and the case-dependent benefits of attention and LP, so it was only helpful when you were looking at different sentences and needed to determine the relationships between parts in those sentences in, for example, machine translation, which is what the transformer architecture was developed for. Question the necessity of attention across various domains. Overall, our results suggest that self-attention is not a necessary ingredient for scaling up machine learning models. With increased data and compute, models with simple spatial interaction mechanisms such as gMLP can be as powerful as transformers, and the capacity allocated to self-attention can either be removed or substantially reduced. So they're suggesting in instances where you don't have two strings and you're sort of like finding correspondences between them, you don't need attention at all. And when you are in that situation, you can have a little bit of attention, but you can remove most of it and replace it with this architecture that has fewer trainable parameters. Yeah, which is, so I haven't read the Fourier transform paper yet. It's in my stack. We'll probably get to it in a bit. I do want to read like a systems paper in here sometime. But yeah, this is exciting. Those of you who watch a lot of the reading group videos know that I'm always like, why do the models gotta be big? They should be smaller. All right, overview of the gMLP architecture with spatial gating unit, SGU. The model consists of a stack of L blocks with identical structure and size. In each block, sorry, this is something in, this is a token in the International Phonetic Alphabet for bilabial clicks, and I don't think that's what they mean here, but that's how that's pronounced in the International Phonetic Alphabet. So this like circle with a dot in it refers to element-wise multiplication of all and in each block. refers to element-wise multiplication, and all projection operations are linear. The input-output format follows BERT for NLP pre-training and fine-tuning, and I don't know what that is, vision model for vision. Unlike transformers, gMLPs do not require positional encodings, nor is it necessary to mask out the paddings during NLP fine-tuning. Attention is position independent, which is why it works the way it does. So you need to add an additional layer to any transformer architecture if you care about order in your output, which usually you do if you're working with language, because you can't just shuffle pieces of language and get meaningful information back out, or at least untransformed information back out. So you don't need that step. And you don't need to mask out the paddings during NLP fine-tuning. So for fine-tuning, you have like a maximum length of input, tokens, strings, whatever, that your system can handle. And the way you do is you find the maximum in your data set that you care about, and then all of the tokens, all of the input sequences that are shorter than that get stuck in this big frame, and then you add just like nothing at the end to make it the right size to go in. If that makes sense. I hope that makes sense. Yeah. Okay, so I'm trying to figure out if I want to try and figure out what this is here, or if I want to read their description first, and I think I want to read their description first and then come back here. But the pseudocode is for the gMLP block. Got a shortcut X. So this is the model. This is the feed-forward network. This is the number of the block, I think. So they're normalizing across the channel, and then they're doing a projection. And then, oh, this is one of those, yeah, I think I want to read their description in words and then come back here and read the pseudocode as well. Pleomax says, does that mean gMLP can have varying length batch input? That's what it sounds like to me. Yeah. What is positional encoding? Yeah, good question. So I mentioned that, the transformer models don't care about order. So the final step in getting the output of a transformer model is that you have this, in the original paper it's trained, and I still don't understand why it needs to be trained, or it's like it's based on some like function transformation that takes all of your tokens and like gives them information about their relationship to each other, because the model never learned that relationship, like spatial relationship to each other, right? Like the apple is red, the order of the words doesn't matter to the transformer architecture, and in order to get output where the order does matter, like it does for humans, the final positional encoding is like, okay, the comes first, apple comes second, is comes third, red comes fourth, and this is their relationship to each other. And yeah, I hope that helps. I think it's on the Kaggle YouTube channel. When I read the transformer paper, I was like, I don't understand why they're making this so hard, and they don't just give things in indexes, but they didn't, and I still don't understand, and maybe if somebody knows, they can let me know. Yeah, so let's read more about their model. So it consists of a stack of L blocks with identical size and structure. Let X be in the set of real numbers n times d, be the token representations with a sequence length n and dimension d. Okay, so this is a matrix. Each block is defined as z is... Is this theta? I think that's theta. It might be sigma. I'm gonna look it up real quick. Sorry for whispering. What does a lowercase sigma look like? Yeah, that's a lowercase sigma. Okay. Yeah, because theta's got like a little tail. Okay. Yeah. Okay, so sigma of xu, where x is this token representation, right? So these are your, your embeddings. your pre-trained embeddings, or whatever they are. I guess you're in the process of training them. So your embeddings, one embedding per token, that's being put in, and then you take the activation function, such as gelu, which is what this one is. And that's from another paper, so that's not new to this one. And then U and V are define linear projections along a channel dimension, the same as those in feed-forward networks of transformers. E.g., their shapes are 768 times 3072 and 3072 times 768 for base. Shortcuts, normalizations, and biases are omitted for brevity. Okay. Yeah. Muse says vectors. Yes, thank you. That is what I was looking for. And sigma. Yes, yes, yes. Thank you. Okay, so what is S? Where's S coming from? All right. So we take our input representation and a linear projection along the channel dimension. Linear projection. I'm just gonna look that up. Channel dimension. Projections into subspaces. All right. So this is just from a MIT math course. We have vector B and a line determined to be vector A. How do we find the point in the line that is closest to B? Intersection, orthogonal, blah, blah, blah. Projection matrix. With X-ray, 3 matrix, not a number. Matrix allocation, not communicative. Column space. Why project? We know the equation may have no solution. The vector is always in the column space of A, and B is unlikely to be in the column space. We project B into vector P in the column space. Because the projection of a vector already on a line through A is just that vector. In general, projection matrices have 3 properties. Okay. I very vaguely remember learning about this, but it has been several minutes, and by minutes I mean years. But it sounds like, you have your multidimensional space. One of those is the channel. Where's the channel dimension comes from? That's what I'm going to look at next, and you just move it over linearly, which I believe they mentioned earlier. What's the channel dimension, Rachel? I'm glad you asked, because I don't know. Channel dimension. Ultrafiltration modules are produced in standard module sizes. I don't think that's what we're looking for. I think this is mechanical engineering. All right. Noted. Channels in computer vision. Channel in a digital image. I'm just on Wikipedia, I'll pop that over. Channel, blah, 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 primary colors. A channel in the context is a grayscale image of the same size as the color image made of just one of these primary colors. Okay. So it's along one of the dimensions, I guess? It's just a dimension. I'm not familiar with what this would be for transformers and MLP, but in computer vision, it would be like red. Also, I believe this group mainly works in computer vision, so I would not be shocked to have a little bit of a computer vision bias in the paper. Whoop. Okay, so what was you? Linear projections along a channel dimension. Same as those in the feed-forward networks and transformers. Okay, so this is just this is a matrix. It's all matrices. I don't know why I'm spending so much time looking it up. It's all just going to be a matrix. Okay, and then S, the key ingredient in the aforementioned formulation is S, a layer which captures spatial interactions, see below. Okay. When S is an identity mapping, the above transformation degenerates into a regular feed-forward network, where individual tokens are processed independently without any cross-token communication. One of our major focuses is therefore to design a good S capable of capturing complex spatial interactions across tokens. Okay, because they're not using a recurrent structure, right? So they don't have the thing where tokens next to each other affect each other because the model is trained sequentially. And they're not using attention, so they don't have the thing where, each token attends to every other token. So how are they going to be able to model interactions between tokens? Basically is what they're saying, and they're using this S. When it's identity mapping, the above transformation degenerates into a regular feed-forward network where individual tokens are processed independently without any cross-token communication. Do I have my tab open? Right, so here, if you look at, like this one, I know it's a little bit small, you can see that in the hidden layer, each item has input from previous layers, but they don't communicate with each other, right? So how do you get information from token to token in this situation is what they're saying, because if there's an identity mapping, you just don't get that, right? You get a normal feed-forward network. You do not get cross-token communication, which is important for things like language, when you need to do things like, I don't know, subject-verb agreement, for example. So the conjugation of the verb depends upon the, person, number, gender, evidentiality of the subject, whatever is relevant for the particular language you're working on. Okay, that makes sense to me. Where's the paper? I'm gonna move it all the way over so I can have it easier to click on. Okay, so they're trying to figure out a way to make sure that we get, interaction between our input tokens and not just a bunch of individual independent tokens. The overall block layout is inspired by inverted bottlenecks, which define S as a spatial depth-wise convolution. Okay, so like in a convolutional neural network, it'll be a sliding window that projects up. No, unlike transformers, our model does not require position embeddings because such information will be captured in S. Okay, so you're getting the information that's in positional embeddings in transformers and in just sort of like picked up by the structure of the network in recurrent neural networks. Or I guess recurrency, recurrentness, the fact of being recurrent. Y'all know what I mean. Our model uses the exact same input and output format as BERT for NLP and VIT for vision. So basically, if you're already using BERT, you can just plug and play their architecture over the BERT architecture. For example, when fine-tuning on language tasks, we concatenate together multiple segments followed by paddings. Okay, so they do assume paddings. Wait. So you don't need them, but you can use them, I think is what they're saying here. Or maybe you don't need the paddings only during fine-tuning, but you do need them for full prediction. But here they say that they are using them. So maybe you don't need them, but they use them. So they're not necessary, but the benefit of doing that is that you would be able to integrate with systems that were already using BERT without having to deal with dimension mismatches. And dimension mismatches are the worst. So that does make sense to me. Okay. So I just need to... lost my chat. There we go. Fabulous. Yeah, interesting. Although many of these protocols were introduced for transformers and hence can be suboptimal for gMLPs, strictly following them helps avoid confounding factors in our experiments and makes our layers more compatible with existing transformer implementations. Okay, so you don't need them, but they use them because it makes everybody's lives easier, and it makes the results more parallel, but they're not necessary. So that makes sense to me. tell me about your spatial gating unit, because this seems like the thing that's really important, right? Because the the MLP is the basic architecture. They're not proposing anything new there. They're like activation. They're using gelu. Somebody else has developed it. That's not new. So what's novel? What's novel is this spatial gating unit, and also replacing the attention in transformer. So, yeah. I was trying to come up with a metaphor from like Lego. And I guess like if you think about like your transformer like a block of Legos, right? They are keeping the same, the same order of the Legos, the same size of the Legos, and what they're changing is that in here there's one type of Lego and they are removing it and they are replacing it with a Lego in a new color that they've just made. So they're yeah, I don't know that was helpful, but that's sort of like where the contribution of this paper is. Santosh says, I guess they don't mask the padding tokens from the loss. They're still just padding. Yeah, I don't think they need to, but they're doing it to make their lives easier. And I mean, if you're currently using transformers, also your lives easier, it sounds like. Yeah. But if you were starting from scratch and you didn't have to have, backward compatibility with a different architecture, you probably wouldn't need to do the padding. All right. Spatial gating units. So this is the, the central thing that they're proposing. To enable cross-token interactions, it's necessary for the layer S to contain a contraction operation over the spatial dimension. The simplistic option would be a linear projection where W is a matrix for which it's the same size as the sequent length. N and B refer to the bias term. So this is the sequence length N, this is the dimension, this is the bias. So this is so far the sort of the basic feed-forward network thing. Which can either be a matrix or a scalar. For example, if the input sequence has 128 tokens, the shape for the spatial projection matrix W would be 128, 128. In this work, we define the spatial interaction unit as the multiplication of its input and the spatially transformed output. So this is, what usually happens in a neuron. And what they were saying, like when there is the case of the identity, which I think we're going to get to in a little bit, it's just a feed-forward network. It's just like a basic MLP. And when it's not, then we get here. So Z is... We were talking about that? What's Z? Each element in Z. So this is a matrix. Okay. Where... the bilabial click denotes element-wise multiplication, okay, of Z, and then the sort of this linear projection of Z, which is the normal thing that would happen in a feed-forward network. For training stability, we find it crucial to initialize W as near 0 values and B is 1, meaning that S is defined in equation 5 is approximately an identity mapping at the beginning of training. This initialization ensures that each gMLP block behaves like a regular feed-forward network at the early stage of training, where each token is processed independently and only gradually injects spatial information across tokens. Cleo says, so they pass the encoded ID directly to a feed-forward network without an embedding layer. Yeah. So this is what they're replacing multi-headed self-attention with. So I don't think they've said like specifically what they're passing in as input yet. I believe, I'm trying to remember the details of the bird architecture. I know they use sentence piece or word piece tokenization, and then I think they start with embeddings. I think you would still start with embeddings. And it sounds like what happens is they start with the basic feed-forward network, and as the model is trained, W. Okay, so this is not W is trained. Okay. Yes. It's all coming to me. So Z is the input. W is trained, and W starts out as being like kind of nothing, just like, whatever. And then as you continue to train and continue to train and continue to train, these weights will be updated based on the relationship between tokens or input items, whatever they are. And as a result, that's where you get the interaction between the tokens and the dependencies and the spatial information. Yeah. Okay. So like how their relationship to each other, basically. I think spatial information. This sounds like a little bit computer vision-y. Yeah. Okay. Meaning the S defining equation 5 is an approximately an identity mapping at the beginning of training. Blah blah blah. The multiplicative gating can be viewed as a mechanism to modulate individual token representations using the spatial signal. In other words, the magnitude for each element in Z can be rapidly attuned according to the gating function. And to begin with, pretty much all the values in the gating function are just 1. Near 0 and B's is 1s, meaning that S defines approximate identity mapping at the beginning of training. Okay. Okay, so this being near 0 means that when you multiply your inputs against this trained value, that's 0. And then when the bias is 1, the output of this is just 1. And then when you're doing element-wise multiplication, you just multiply everything in Z by 1. And then as time goes on, and as the weights in the W matrix get updated, suddenly the element-wise multiplication, some things might be more than 1, some things might be less than 1, so you're going to get sort of an attention-like effect where some weights are increasing and some weights are decreasing over time. Okay, that makes sense. Amina says BERT starts with embedding. Yeah, thank you. Helpful. I feel like it's glove, but that's just like, that's based on nothing. I would not bet on that. Okay. That makes sense to me. So the gating mechanism is changing the input weights, and then those are passed on to the next layer, and these are stacked. So that happens a bunch of times. Yeah. Hector HSC says, what is your doctorate in? My doctorate is from a linguistics department, and my specific research area was computational sociolinguistics. So basically, using NLP to ask questions about how people's social identities affect the ways that they produce and perceive language use, and also how people in computational contexts, how their social identity affects the ways that they produce and perceive language, basically. Good question. I'm always happy to talk about my PhD. It was a fun time. All right, so this makes sense to me. We further find it effective to split Z into 2 independent parts, Z1, Z2, along the channel dimension for the gating function and for multiplicative bypass, as is typically done in GLUs. Okay, so this would be like, you've got your R, G, and B. You do the G separately, you do the B separately, you do the R separately. I guess. I don't know what the channel dimension would be for speech or like text. I do not know. We also normalize the input FWB, which empirically improves the stability of large NLP models. this gives us the unit illustrated in figure 1, which we refer to as the spatial gating unit in the rest of the paper. In table 3, we provide ablation studies to compare SGU with several other variants of S, showing that it works better and narrows the performance gap with self-attention. So they tried a bunch of stuff, and this is the one that worked best. Yeah, you're very welcome, Hector. So that's this, right? So this one is the spatial gating unit. So normalization, protection, and then, you know, doing the my brain keeps giving me the word attention, and that's not the word that I'm looking for. Nope, I just keep getting the word attention. Again, that's not the word I'm looking for. And then you do the spatial gating unit, and then the final projection. So except for the spatial gating unit, this is you know, your basic MLP feed-forward network. No, sorry, I look at that word and my brain's like, attention! Attention's the word you're looking for. It's not. And then within the spatial gating unit, they split for channel. So this is just something they said empirically works better for NLP tasks. And then the normalization of V, which is 1/2 of it. And then they get the dimensions of V. And then they do the projection of it plus the bias. So V here is the linear projection along the channel dimension. Oh, I see. Okay, so they're projecting along one channel, and then later they project along a second channel. Okay, and if we come down a little bit further, V is not here because what they've done is that they have split up U. So here, what's W here is V and U up here, I think. The activation, thank you. Not attention, activation. Brain, Jiminy Cricket. I'll finish my coffee and maybe that'll help. Okay, so linear projection across the channel dimension with just splitting in half. So that's why there's 2 of them instead of just 1. And X is the token representations. So this is the token representations. This is the matrix, half of it, along the channel dimension. And then to take the output of that sort of like basic feed forward, and then they do their gated attention. No, all of that happens inside of here. So this S of Z is this one, right? This whole thing, which incorporates both the regular feed-forward network and then also the, so it takes the output of the regular feed-forward network and then multiplies it by the learned matrix, and then it helps to split it into 2 bits so that there's 2 of them. I'm getting confused about what's what here. Hi, Krim. Santush says, my guess is the channel detection. Channel dimension is the length of the layer. So the layer dimension? Yeah, that could be. Okay. I think I have a broad conceptual understanding of what they're doing. I don't think I have a good mapping between what all of these... I don't think I have a good mapping between which parts of my conceptual understanding each of the letters map to. So that's where I am right now. And I think that really it's the splitting along the channel dimension that's causing me to be confused here. So this, all of this bit, right, is in the spatial gating unit, and they have split them. Okay, I see. So only half of, so they split along the channel dimension, only one of the channel dimensions gets this process done to it, and then they multiply the output by the, yeah, and then they multiply the output by the other channel. So this is like a little bit of like a normalization thing. Okay, I think I'm picking up what they're putting down. Hopefully. Maybe they put something down and I'm picking up something just beside it, which sometimes happens. Remark. And the guess for the spatial dimension is the number of tokens. Okay, so they've got the... Yeah, I agree. I think the spatial dimension is the number of tokens. Which I think this makes more sense if you are talking about pictures than if you're talking about language input, but I'm never talking about pictures, so that's where I'm coming from, and that's my own bias. Remark. The overall formulation of spatial gating units is closely related to gated linear units. A key distinction is that our gating is computed based on the spatial cross-token dimension rather than the channel per token dimension. Wait. So you've got, okay, so I think in a language instance, the channels are, you have your embedding matrix, right? For each token, you have your input embedding. I think the channels are the words in your embedding, if you're using words, the tokens in your embedding. And then the spatial is the relationship across them. So the multi-channel thing would be splitting, half of the words get gated and the other half don't for each layer, and then I'm guessing that some layers get one channel and some layers get the other. Maybe. Maybe they'll talk more about it in the MLP section. It also resembles squeeze and excite blocks. That's an awful name. I don't like that. In terms of element-wise multiplicative interaction, but instead of doing pulling, SGU allows learnable spatial transformations. The spatial projection in SGU could learn to express superficial depth-wise convolutions. Unlike typical depth-wise convolutions with channel-specific filters, SGU learns only a single transformation and shares it across channels. Ooh, one sec, gonna block somebody. Ooh. My guess is the channel dimensions for words is the embedding vector dimension. Based on this, I think the channel is like the tokens. Like each token is a separate channel, so they're like splitting the tokens in half, and half of them get gated and half of them don't. Could be wrong about that. I think the embedding vector dimension makes more sense. So that like half of the embedding gets updated and the other half doesn't, but maybe that's not what they're doing. Channel doesn't make a lot of sense when you're talking about language input, and I think that's just where my confusion is coming from, because I would probably say like the token dimension and the embedding dimension rather than channels. Finally, we note that SGUs offer an alternative way to capture high-order relationships other than self-attention. Specifically, the output for equation 5 contains up to second-order interactions, e.g. Zi, Zj, and the output for self-attention, assuming nonlinearity, contains up to third-order interactions, Zi, Zj, Zk, because of the key value. What's the third one? Query interaction. In terms of computation costs, SGU has n to the second e divided by 2 multiply adds, which is compared to 2 n squared d of dot product attention. Both are linear over the input channel size and quadratic over the sequence length n. So basically what they're saying here is a lot of things, but the thing that's important for me is that the um, computation cost, woo-wee, the computation cost of these spatial gated units are far lower than the computation cost of dot product attention. Not least because you're working in one fewer dimensions, right? You've got second order rather than third order interactions. Yeah. Whew. This is making my brain tired. I think I want to pick up with this again next week because I think there's a lot here, and I would love to dig into it a little more because I think we're going to see more papers like this. Although let me double check that this is actually like there's going to be enough space that it makes sense for us to do that. Yeah, I think there is. I think there's enough here that it makes sense for us to pick up with this next week because I'm probably going to spend a lot of next week trying to like remember what all the numbers mean, all the letters mean. Yes, and that's about as much math as I can handle in one staring at the screen session. Yeah. So top order takeaways, or I guess top line takeaways, the computation cost of the spatial gated units is way, way lower. It's a sort of slightly different option than your other types of gated units. Because you have the interaction between different tokens, they can affect each other in the final, like there's information shared between tokens, right? Or at least weights. Also, I can't remember the word activation to save my mundane life. Yeah, so I think things that are exciting to me, like as a practitioner, lower computational cost, love to hear it. Being able to get comparable results sounds really good. We'll take a little bit more of a peek at that next week, and talk a little bit more about sort of what their discussion of the applications are. Yeah, and you don't need attention, I think is the big point of this paper. And I think it's interesting because I think at some level when we talk about attention and like when I describe attention at a very high level, I think that this type of shared information is what people think attention is. And I think that at least conceptually, this is very similar, but the number of weights you need is much lower and the number of trainable parameters is much lower, which I'm excited by. I love small models. Make them smaller. Did they release source code? Yes. So the link, I'll pop it in the Twitch. The link in the YouTube is to papers with code. And there is a bunch of code that's been made available. Although I would be surprised if any of these were by the Google team because they're all in PyTorch, and I know that Google Research tends to use TensorFlow for perhaps obvious reasons. But yeah. I would be surprised if they didn't have some code available because they have the pseudocode available, so why wouldn't they? Yeah. All right, so that's where we are now. We'll come back next week and talk a little bit less about the model architecture and a little bit more about their implementation with BERT and sort of their findings there. I do think it is interesting that some attention does seem to be necessary for, being able to describe relationships between sequences, which makes sense because that's what machine translation is usually broken down into. And transformers were proposed for machine translation, so they may be especially fit to purpose, but you don't need them everywhere. Yeah. All right, so we'll be back next week with the second half of this paper. We're not going to read the vision stuff. I don't think it would be valuable for anyone if I tried to slog through the vision parts. And then tomorrow we're going to come back with live coding. So I've been working on just like a a bot to answer the questions that I get a lot. And like, since we took a little break to work on some visualization stuff, I got people on Twitter asking me the questions that the bot could answer like a couple of times. I was like, all right, I'm gonna finish this up. So that is my plan for next week, for tomorrow, and maybe we'll get it launched, maybe we won't. It really depends on like how much I have to futz around with Docker. So yeah, hope to see you then. If you haven't signed up for L3AI yet, please do that. It's free, it's online, we'd love to have you. There's gonna be a bunch of great talks. I'm giving a talk on topic TBD. It depends on how much time I have to develop talks. And it's l3-ai.dev if you are interested. Yeah. So thanks for joining. I'll see y'all tomorrow for live coding, and then next Wednesday for office hours, and next Thursday to finish the paper. And I'll talk to you then.